Hi everyone, back again. So just a nice little symmetry here with our diagram about these ratios. Now you may have noticed in the previous video, what's all these red triangles doing over here at the side? So the idea is we have theta down here in the corner as defined previously. Now using of course the idea that the x and the y-axis are perpendicular, this small angle here that I've just marked should be the complement of theta. And so the sine of the complement of theta, the cosine of theta, there it is. It's the opposite side over the hypotenuse of 1. That red line marked cosine theta, which of course would equal the x coordinate like we saw a moment ago. And in the same way that we saw tan and secant matched, then the corresponding parts of these red triangles, the complementary angle to theta, the tan of the complement or the cotangent, would be this segment here from point E to point A, and the complementary angle, the secant of the complementary, would be this red line from point E down to point O. So it's a nice symmetry here that the blue triangles are the sine ratio, the tan ratio, and the secant ratio, and the red triangles are the complementary ones, the cosine ratio, the cotangent, and the cosecant. It's just a nice way to remember, I suppose, how they all fit together. Now, I promised that this one was going to be about the Pythagorean theorem. So remembering, of course, that the distance OC would be the x coordinate of our point, and the AC distance would be the y coordinate, then all of us know, of course, that Pythagoras says x squared plus y squared equals 1 squared, because we have a right triangle here with side of x and y and hypotenuse of 1. Now, let's use what we had for trig ratios. X was the cosine of theta, so cosine squared theta. Y was the sine of theta, sine squared theta. That's our first expression of the Pythagorean theorem, right there. Now let's do something interesting. Let's divide everything by, well, let's say cosine squared. So my first term would be cosine squared theta divided by cosine squared theta. My second term would be sine squared theta divided by cosine squared theta. And my last one is 1 divided by cosine squared theta. So it's the original theorem, everything divided by cosine squared. Now what happens? All of that cancels to give 1. Sine squared over cosine squared. We saw last time that sine over cosine is the same as tan. And if I were to remove the expression for squared like that and write it as sine over cosine squared, you can see that it's tan squared. And 1 divided by cosine squared. Now remember from back up here, 1 divided by cosine is the same as secant. So that is sec squared theta. That's still the Pythagorean theorem, but expressed in an alternative way, because it came from the same starting point. Let's do this a third time. Let's start again with cosine squared theta plus sine squared theta equals 1. Last time we divided by cosine squared. This time let's divide by sine squared theta. Divide by sine squared theta and divide by sine squared theta. All of that cancels to leave 1. Cosine squared over sine squared. Again, if I express this, oops, rubbed out my vinculum line. If I express this as cosine divided by sine, then I hope we'll remember that that is cot squared theta. And remember, 1 over sine is the same as cosecant, or cosec. So this is cosec squared theta. This is still the Pythagorean theorem, but expressed as a third different way. Now, let's go and look at our diagram. If I look at this right angle triangle here, I would have 1 squared plus tan squared equals secant squared. That's this one. 1 squared plus tan squared equals secant squared. Comes from the big blue right angle triangle. How interesting. What if I look at, different colour this time, what if I look at this triangle? Now this is a right angle triangle. I have a radius here of 1. I have a tangent line, so there's the perpendicular. I would have 1 squared plus cot squared equals cosec squared. There we go. 1 squared plus cot squared equals cosec squared. The Pythagorean theorem appears in the triangle here with the complementary ratios. Isn't that interesting? And of course, the original one appeared from our first little triangle here with x and y and 1. So that is the 3 different versions of the Pythagorean theorem using the trig ratios and the inverse trigonometric ratios.